All right. Yeah. Thanks a lot, Matt and Vala, for the invitation to give that seminar. So for me, that field of superconducting diodes is relatively new, so I learned a lot from the seminar already. And also, I want to point out immediately that within the scope of our work, we never actually thought of creating a superconducting diode, but then we realized that a lot of the ingredients which were discussed here, like inversion symmetry breaking, time reversal symmetry breaking, can be induced by interactions in sort of our platform of study in magic angle bilayer graphene. So, okay, and that's why I'll talk a little bit about broken symmetries in magic angle bilayer graphene and superconducting diodes that we find in gate-induced Josephson junctions of these magic angle bilayers. And before I start with the physics, really just a quick intro to who we are. So yeah, we were a group at ICFO Barcelona for the last couple of years. But basically this summer, we are moving to LMU Munich, where we are going to have a slightly larger group. And where we are also a part of the Munich Quantum Valley and Munich Center of Quantum Science and Technology. So we are having our move this summer, and our lab should be operational in October. So if you know anybody who looks for positions, so we have several positions on all the different levels. Also, I want to say that we're very thankful for theory collaborators, in particular Andre Bernovic was instrumental to the work, and Katie Lowe. And also Eli Zeldorf and Weizmann Institute, who helped us to characterize some of these devices. And so really, just an introduction. So I forgot to remove that lower comment, but this will come next. But so, okay, twisted bilayer graphene, probably many of you have heard about this by now. This is basically a new platform to study strong correlations, and really surprisingly, many exotic phases that are usually just common for systems like the cuprates or heavy fermion systems and so on are found also in this material species. In particular, of course, most interesting the superconducting phase, which at this point probably by most theorists is believed to be unconventional. But of course, not just superconductivity, it has correlated insulator phases, orbital magnetism, topological, non-trivial topological properties, strange metallicity, etc. And really, since the field was sort of opened up by Pablo Ferrero in 2018, there have been a number of works on that particular platform and graphene. But of course, there are many other platforms such as TMD, twisted TMD materials, and so on. And really, just to give you some specialty about the system is that it really offers some intermediate scale and intermediate energy range platform from correlated physics. So of course, as we know from crystals, such as cuprates, for example, all these phases are observed in these, but however, sort of the interaction length scales basically defined by the lattice side are in the order of angstroms. So the electrons sit angstroms apart from one another, which of course defines large interaction energy in the order of EV. And of course, another prominent example of such systems is our optical lattices, where everything is stretched out to micrometer scales, and also the interaction energies are extremely low in the pico-electron volt. So really, twistronic materials here, like magic angle graphene, they offer some sweet spot here. They offer intermediate length scales and intermediate energies. And of course, they also offer new ways to manipulate the materials. So, which I will not talk about it in detail, but because we create these heterostructures, there are entirely novel ways how to sort of assemble and to manipulate these material species. And just to give you sort of a glimpse of how the material behaves, this is a phase diagram of a typical, not a typical, but one of the nicest samples we made, where we basically can see all the different phases in one device, gate tunable from one another, and you can tune in these phases in and out by applying magnetic fields or applying gates, for example. And so this is a typical map. So this shows, so what we measure is two-terminal resistivity. So here red regions are high resistance and blue regions are low resistance. And also we measure usually these resistance as a function of carrier density. So by applying a gate voltage to the graphene device, we can change the carrier concentration continuously. And we can, for example, fill up the bands completely, or we can empty them completely. So we can really sweep through this phase diagram, and we can completely empty a band, which is here on the left corner side, up to when we completely fill it. And so what we see here is the following. So for example, here, these ultra bright red regions, which appear at exactly integer fillings of electrons or holes per Moray lattice site, those are correlated insulators. And those are basically insulators similar to MOT insulators, which are given by the strong electronic interaction between the electrons. Then, as you can see, flanking such a correlated insulator is a very sharp superconducting dome, which can have TCs up to 5 Kelvin sometimes, in the best cases. In this particular case, 3.5 Kelvin. And of course, it also shows all the other signatures of superconductivity that were defined elsewhere. In the center of the band, we also see strange metal behavior, where basically the resistance follows a linear temperature dependence and has a Planckian dissipation. So basically, the electrons scatter as fast as allowed by the Heisenberg uncertainty principle. Then at another filling here, filling factor 1, which corresponds to 1 electron per Moray unit cell, we see basically magnetic hysteresis. So if we measure the RXY signal as a function of the magnetic field direction, whether we sweep it up or down, we can see this sort of hysteresis loop appearing, which, by the way, is also almost quantized. So RXY here is close to being quantized to 1h over e squared. So in some other works, it has been really shown that these states are perfectly quantized. And then, of course, there are also a number of works which reported Chern insulator in the systems, which basically means that we have topological states which typically appear at slightly elevated magnetic fields. So you need some magnetic field to break C2C symmetry. But in principle, these states also often go all the way down to zero field. And these are basically also the states which give rise to this orbital magnetic states and zero field Chern insulators. Okay, so having all these phases together, I just want to first go to explain the Chern insulators orbital magnetism, which we find in the system. And really, I want to start by explaining a little bit sort of the band structures and band topologies that are present in the system. And so first of all, the bands which we are dealing with in magic and graphene, they are extremely flat. So these flat bands are in the order of 10 MeV. They are separated by larger band gaps to higher order dispersive bands. And because these bands are so flat, the kinetic energy is almost zero. And the dominant energy in the Hamiltonian becomes the interaction energy U. So this explains, for example, all the strongly correlated physics and the strong interactions. But moreover, these bands are also topologically non-trivial. So if one in detail looks at sort of or analyzes the topological properties of these bands, in particular, one starts basically at the mini beryllium zones, which are created in the corners of the K and K prime valleys. These mini beryllium zones are separated by a large sort of K space, so they're almost decoupled. And in contrast to single layer graphene, these sort of beryllium zones, they have a non-zero total helicity. So if you look at each of the mini beryllium zones, they have a plus or a minus 2 total helicity. which means that one cannot find localized one-year functions to this problem, and the bands naturally have to be Chern bands, or in other words, topological Chern bands. So the Chern bands come in a sort of, there are overall 8 Chern bands with basically Chern numbers 1 on -1. So the orbitals here are defined below. So we can, if we analyze this, we can define 4 Chern bands with a Chern number of -1 and 4 Chern bands with a Chern number of 1. So for example, if you have a spin up K prime valley and a sublattice, then it's a Chern number of -1. Whereas if you have a spin down and a K prime valley and a B sublattice, you have a Chern number of -1. And again, so the quantum numbers here are spin, valley, and sublattice. What's funny about it is that when you look at these bands together, they're exactly at the same energy to one another, and they're perfectly degenerate. So whenever you measure transport properties, these bands are always degenerate, and you are not seeing any topological properties because the total Chern number is always 0. So what you need to do now in order to resolve these bands is you have to break inversion or time reversal symmetry. So you, in order to lift the Dirac points and to gap out the system, and so basically, therefore, to polarize these Chern bands with respect to one another. And there have been a number of theoretical work on this. So there are really a number of sort of bases and ground states which have been proposed to think about this problem. And what we know, just to give you sort of a glimpse of what's happening. So if we start, for example, by breaking a single particle inversion symmetry C2, this, for example, has been done by several groups which align twisted bilayer graphene on HBN substrates. This basically on a single particle level breaks C2 symmetry, and it the valleys become asymmetric. So if we look, for example, at filling factor 0, so the charge neutrality point ground state for such a symmetry broken state, it naturally would have a Chern number of 0, and the sort of population of the Chern bands in the different valleys is exactly opposite to one another. In contrast, if we would start with time reversal symmetry, we would get the opposite picture where the valleys are symmetric, and therefore the Chern number of a charge neutrality point state would have a Chern number of 4. So it's experimentally, of course, one can observe such differences quite easily. And of course, how can we break time reversal symmetry? By applying magnetic field. This is sort of the simple answer. And of course, in principle, also the interactions and in zero magnetic field can break time reversal symmetry for you. So I will show both examples of how we achieve those states. And so here I'm basically showing you some results which have been obtained by our group when we applied a strong magnetic field to these twisted bilayer devices. So the field is, of course, out of plane. And what we really see is that we see a very strong sequence of Chern insulators where there's really one Chern insulator appearing from each filling factor, and each filling factor gives you a different Chern number. So we get this robust sequence of a Chern number 4 Chern insulator appearing from filling factor 0, Chern number 3 insulator from filling factor 1, a Chern number 2 insulator from filling factor 2, and so on. And of course, so what I'm showing here is basically the longitudinal resistance, the function of magnetic field. So the blue regions are the regions where the resistance is 0. And we really extract the Chern number from the strata formula, which basically dictates that the slope of a Chern insulator in this density versus magnetic field phase diagram should be proportional to the Chern number of the state. And so really just from the slopes of these 0 resistance regions, we can extract the Chern insulator, the Chern numbers. But of course, Also, we can measure sigma xy, so the longitudinal, the Hall conductivity. And we also find quantized Hall conductivity corresponding to the exactly same Chern numbers in these states. So, and this was worked out, of course, not just by our group, but many other groups, alias Dani, Andrea Young, Stefan Natschberge, Eva Andre, Pablo Jairo Ferreira, of course. They have had also a similar sort of results on this. And really another sort of proof that these are really interaction-driven Chern insulators, so not just time reversal symmetry is responsible here, but maybe interactions, is that really we typically get much bigger energy gaps than for typical Landau levels. So this we can measure with temperature-activated transport. Again, we usually have much lower quantization fields for these states than for Landau levels, often down to zero magnetic field, as I mentioned. And for example, STM measurements, they also have shown interaction-induced spectral broadening of these states, which is typically a signature that interactions are really strong, strong drivers in these states. So without going too much into detail, so I think this is really strong evidence. Of course, now we are at the state where we can identify many of these states in much more detail. But what I want really to focus on is that really some of these Chern insulating states, they are persisting down to zero magnetic field. And so here we see such an example. So here at a filling factor 1, we see a Chern insulator 3, just as described before, which persists all the way, almost all the way down to zero field. And actually at zero field, we see that a Chern number 1 orbital magnet is developing, right? So, and again, this Chern number 1 is basically identified by a close to quantized Hall resistance with respect to the sweeping direction of the magnetic field, but of course it's also defined by the slope it takes in the density versus magnetic field phase space. And so without going into detail, one thing I want to mention about these magnetic zero field magnetic states is that these states are quite disordered. And that these states usually form a Chern mosaic of all the different Chern numbers. So for example, those are images of scanning slit microscopy performed at Elie Zeldov's group on this very particular device, which I just showed you with the magnetic state in it. And really these magnetic states form a rather disordered domain wall structure, where Chern numbers of 1 and Chern number of -1 can coexist next to one another. And also even Chern number 0 states are possible, which is explained by some sort of local alignment with the HBN substrate. Okay, so this is really just to give a little bit of an explanation about what states are present in twisted bilayer graphene and what type of symmetry breaking is basically happening in order to achieve those states. And now I really want to go now to the superconducting diode sort of measurements and basically use these states to explain the behavior which we observe. And so one thing we can do is with these devices, as I explained before, taking this phase diagram, which I showed you in the very beginning, what we can do is we can gate tunably sweep between different phases. So I showed you that here in this corner at a filling factor of -2, we have a superconducting state. And then really just by tuning the gate, but just by applying a voltage from this gate, we can continuously tune into this orbital magnet, which is again also topological in nature, which resides at a filling factor of 1. So okay, so how cool could it be that we can now hybridize those states together? And this is exactly what we tried to do. So basically, there were already some previous results by the group of Klaus Enstein and by Pablo Ferro, who showed that you can gate define Josephson junctions in twisted bilayer graphene. However, we went slightly different directions. So we made these devices, which are these quintuple stacks of van der Waals heterostructures, where in the center we have twisted bilayer graphene encapsulated in HBN. HBN is just an insulator for the sake of what we want to know about it. And on top and on the bottom, we have these graphite gates, and graphite really for us is just a normal metal. And you can see, so the devices are not tuned completely homogeneously, but the top graphite gate has basically a split. So those are basically split gates that we have on top. And so what we can do is now, by choosing the right sequence of top and bottom gate voltages, which I will not go into much detail, we can locally tune the center region of the device into a different carrier concentration than the side, basically the leads of the device. So we can, or in other words, we can even fix the leads to a certain superconducting position, for example, and then we can sweep the center region into any other state which is given in the phase diagram of twisted bilayer graphene. And so the right-hand side image here shows you a little bit of how it works. So for example, we can find on our RxX versus filling factor map, we can find a superconductor here, which is this region where resistance drops to 0. And we can fix the sides of the device to the superconducting region. However, the central region here, the junction region, if you want, we can tune it into any other state. In particular, we can tune it, for example, into ferromagnetic or orbital magnetic state, which we can find along the way. Okay, and so how do the junctions, how do the transport measurements look like? So basically, this is a map which shows dVdI as a function of current and as a function of Nj. So again, this is the density of the central region here. And the leads of the junction, they are tuned into the center of the superconducting dome. And so, in other words, you can also trace Nj here on the top image. So here it shows Rxx as a function of Nj, right? And we can see where the center region is in the superconductor and where the center region is, for example, in a normal metallic state, or when it enters one of those correlated insulators in the minus, for example, here at the -2 Moiré holes per Moiré filling. And so what's interesting now is really to see how the dVdI as a function of magnetic field look like. So for example, here in this point in the center, where a perfect SSS region is formed. So we basically, in principle, form a homogeneous superconductor. So the leads and the center regions are in the superconducting state. And we see this typical diamond-shaped pattern without any Frauenhofer interference, where typically, this is very typical for all the sort of non-junction superconducting devices, where we get a critical current in the orders of a few hundred nanoamps. And of course, with magnetic field, these diamond also closes with a critical magnetic field in the order of few tens or to hundreds of millitesla. So this really looks just a normal homogeneous superconductor twisted bilayer. Then we can tune here in the normal region. So again, this is now forming a real Josephson junction. So this is a SNS region. So this is, of course, first proof that the junction is really created by this gate tuning. So this is good news. And if you look at the junction is relatively symmetric with respect to the current direction and the magnetic field direction. And this is really comparable to the junctions which were created, for example, by the group of Klaus Enstein or Pablo. So, but the funny thing is what is happening now when we tune the junction into the close to the correlated insulator, where again, magnetic and Chern insulators were reported before. What we can see is that the junction looks really quite differently than a traditional Frauenhofer pattern should look like, and it also looks quite differently than in the case of the FNH. And really to start understanding what is going on here, we can start immediately looking at sort of its properties with respect to the field direction sweeps and with respect to sort of pre-polarizing the junction and depolarizing it. And so I just want to zoom in on this image and really explain that, for example, if we measure the VDI signal as a function of magnetic field, ramping the field in one direction versus ramping the field the other direction, this is this image here. You can see so that the Fraunhofer somehow flips. So it becomes, it really, after you sweep it in one direction and sweep it back, it flips, it becomes sort of antisymmetric to one another. And not only does it flip, but it also develops some sort of phase shift to one another. And same sort of trick we can do by looking at the direction of the current sweep. When we, for example, pre-magnetize a junction into the plus or the minus magnetic field direction. So we apply a pulse of 30 millitesla, we take a current sweep, and then we can apply minus 30 millitesla and take a sweep back. And so, as you can see, also the DVDI characteristics is a function of these pre-magnetization. They're entirely flipped, and in particular, you already see that there is a symmetry developing with respect to the critical current, whether we're sweeping, whether we're pre-magnetizing one direction or the other. Okay, and this, of course, to us smelled immediately like magnetic Josephson junction, and so we wanted to really be a little bit more sure about that. So first of all, what we can say is that whenever we look at the left graph here and the black curve here, whenever we perform our first measurement of the VDY, when we just cooled the sample down, we take a look at the measurement, and it's perfectly symmetric with respect to the current direction. So there's no asymmetry developing whatsoever. And this asymmetry really develops only when we start applying a magnetic field, which is higher than some sort of coercive field for the given magnet. And so if we apply 500 millitesla, it becomes asymmetric to the negative current direction. If we apply a negative magnetic field, it basically get tilted in the other direction. And if we warm up the system and cool it down again, we start back at the black line here. So all sort of magnetization is erased. The other thing, what is interesting is that if we take now these Fraunhofers, by always sweeping the magnetic field up versus the Fraunhofer by always sweeping the magnetic field down, we can see that the entire Fraunhofer pattern switches somehow its symmetry, and it also develops really strong phase shift to one another. So really looking at the differences between these line cuts that we can take from these Fraunhofer patterns, we can really define a delta B, sort of a phase shift between the Fraunhofers swept in these directions. And these phase shift as a function of temperature, it really follows some sort of critical behavior with a TC of around 800 millikelvin. And this is really much smaller than, for example, the TC of the superconductor. So in this particular case, TC of the superconductor was around 3 Kelvin. And the TC of the alleged sort of magnetic phase that we trap in the JJ is much lower. It's in the orders of below 1 Kelvin. Okay, and so really without going too much into detail on that, so what we believe, and this is what we worked out with Katie Law, our theory collaborator, we believe one state explains these findings really well. which doesn't mean that other states would not explain it also, but at least this is probably the simplest possible state you can construct for a Chern number -2, for a Chern number -2. And this is basically just a valley polarized state where, again, we have a valley polarized valley. In one valley, we have two Chern numbers, Chern bands filled up. This gives you a total Chern number of -2. And the other valley is basically not filled up at all. This is how the state looks like. So for such valley polarized states, always you end up having some sort of orbital currents. Of course, you can calculate also the magnetization of such an orbital current. And so they calculated that the magnetization for these states is around 10 Bohr magnetron per mole, sort of for the brilliant zone here. This gives us something quantitative now to look in our measurements. And last but not least, so for these type of orbital magnets, there were a number of previous work by various groups. For example, by the group of Andrea Young, they found that there is also a current-induced effect in the switching of these orbital magnets. So depending on the magnetic field, the current direction, you can switch the orbital magnetization direction. So you can, by applying a positive magnetic field, you can switch the magnet to a out of plane positive direction. And by applying a negative current, you can switch it back to a negative direction. So it was really shown that there is really a coupling of the current and magnetization in such orbital magnets. And really, we can now a little bit quantify our findings, therefore. So first of all, these findings explain the phase shifted Frauenhofers that we observe. So if we ever look at sort of a trace of a positive current direction as a function of magnetic field, then usually our zeroth order Fraunhofer peak is never at zero magnetic field, but it's shifted slightly away from it, usually in the orders of 3 to 4 Bohr magnetrons. So we're not so far
Dima,
away.
I just want to remind you that technically now you're in the question and answer time. So
yeah,
hopefully we can wrap up in a couple of minutes.
And I'm almost done. Yeah, thank you. Right. So so basically, this phase shift is explained relatively well by the magnetic field that we are applying, but by the magnetization that is applied here. However, of course, we don't reach 10 Bohr magnetron, but this is, I guess, probably because of this domain wall structure. And then also, of course, we observe really in these measurements, we observe a clear asymmetry between the current directions, and we observe a phase shift depending on which whether we sweep the current up or we sweep the current down. Okay, so again, as I mentioned in the beginning of my talk, we were never really intending to study diode effects, but of course, and this is my last slide, of course, to summarize all of that, of course, sort of in the end of writing the paper, we also saw all those papers which have been published in the field of diode superconductors, and we realized that indeed, so this sort of effects which we obtain when we pre-magnetize our junctions. So if we pre-magnetize our junctions to 50 millitesla, we get sort of a symmetric DVDI to the positive critical current direction. And we do the opposite, we get it to a negative critical current direction. Of course, it opens up a window where of sort of current where we are superconducting in one direction, but not superconducting in the other direction. And of course, we can apply, for example, a current to change, to switch these effects, but we also can, of course, apply a magnetic field, and we can really change sort of the direction of the superconducting diode with this magnetic field. And with this, that's all. I thank you for your attention, and I'm happy to answer any questions.
So thank you very much, Dima. And I think the floor is open for questions for the next like 5-10 minutes. So I think we have one in the chat actually, so I'll read it out loud. Your Frauenhofer pattern looks like an asymmetric squid. Can you comment on ruling out self-inductance as a cause for the effect?
So, okay, so asymmetric squid. So how would how would self-inductance play into the squid? So first of all, I mean, I'm just saying that the junction geometry is definitely very different than what you expect from a squid. So I think there are, of course, possibilities that for these orbital magnetic states, we might also have edge states, which are basically contributing to the conduction. And then, of course, if the bulk is somehow insulating, basically this orbital magnetic state is insulating in the bulk, and we have edge conduction, then we would think of creating a squid. So this is something which is a possibility.
Dima, you'd have a squid even if they weren't insulating. Just having even a bulk conductor with also conducting edge states will result in a squid.
Exactly. So so we have thought about basically again, as I mentioned before, those edge states are supposed to be present here as well. So you could have non-homogeneous current across the NJ region with edge states formed there. We have not found any other evidence at this point for these edge states in these states. So in this particular device, I mean, so we can perform transport measurements on other regions.
I think the question is also just kind of generally asking, if I interpret it correctly, about like self field and how you rule out things like that.
Mm-hmm.
So Dima, a DC squid with an inductance that's different on both sides will also exhibit a diode effect. Okay. And I think the question is asking, can you be sure that it's not something like that?
And so I'm just wondering how would that and so in the given device geometry, how would that play out? So yeah, I'm a little unsure about that. Yeah, but this is something.
Maybe this is a good discussion section question, since it seems to not be a short answer, huh?
Yeah.
Jia Cheng we'll come back to that question if you don't mind, and maybe we'll take another one. Hung, I see a hand raised.
Thank you for your talk. Actually, I have two questions. First is, if I understand correctly, you ascribe the shift of the Frauenhofer pattern to the magnetization of the twisted bilayer graphene. But previously, as you characterize the magnetization of the twisted graphene, you use the delta B, and it means between two peaks of the IC. So what's the difference between these two kind of magnetization?
So okay, so this is a very detailed question, exactly. So let me just go here, right? So in principle, looking at the state which we are proposing, there are basically two sorts of magnetism that you can think of developing here, right? So first of all, you can have the orbital magnetization, which arises because of the valley symmetry breaking here, right? Is basically just this sort of K and K prime imbalance that gives you just orbital magnetization. But in principle, also, of course, that each different Chern band also has a different spin orientation as well, right? So in principle, you could, at lower temperatures, you could also start polarizing the magnetic, the spin degrees of freedom here as well. So what we think, and this is in detail, I didn't go into much detail here yet, but this is written in detail in the paper. What we think is that there are two things happening, really. So there is one thing which happens basically when with a TC of 3 Kelvin. So basically, whenever we form the superconductor, we start seeing that effect. This is basically the general asymmetry of the Frauenhofer pattern. So if this I versus D asymmetry, we start seeing it at really elevated temperatures, and this is basically something which we see all the time here. This, I think, this asymmetry we attribute to the orbital sort of magnetization part. Then this hysteresis, the hysteretic jumps, this is something which we start seeing then at much lower temperatures with around 800 millikelvin. And this is something which is still a point of debate, but we really have the feeling those are the two effects which I described. That there is this orbital degree of freedom, but then there's also the spin degree of freedom, which can give you such phase shifts as well.
Yeah, okay, thank you. And my second question is, in the Frauenhofer pattern in your SNS region, could you show that slide? Could you go back to that slide?
This one?
Yeah, no, next one. Yeah, this one. In the figure E. If we look very closely, it seems like the Frauenhofer pattern also shifted towards zero. I mean, towards the negative field a little bit. Does that mean there's also the magnetization influence this shift of the Frauenhofer pattern?
Yeah, I mean, in principle, so the -3 state is also supposed to be magnetic. So all of the, as I mentioned, all of the integer fillings have some sort of spin and basically SU4 symmetry broken states, and they all of these integer fillings can give you some of these behaviors. The nature of each integer filling state is, however, still a debate, and there are all different possibilities that are being debated right now.
Yeah. Okay. Thank you.
Yeah. But so, for example, just to also give you an idea, so right, I mean, the magnetic state which we found in this device was a +1, right? Yeah. So in principle, yeah.
Okay, thank you very much, Hung.
Thank you.
Martin is making more of a comment, I think, than a question, if I understand. He's responding to Jie Cheng, so not to Dmitri. So maybe I'll just ask one last broad question, and then we can end the session. So zooming out a little bit, Dima. So we've learned in the last couple of days that there are many ways to cook this chicken here to make a superconducting diode effect, right? And if in the most basic general terms, it seems we want to break inversion symmetry, and then have, you know, some reason, let's say spin orbit coupling, some effect, right, to get the spin splitting, and then some way to break time reversal, often, although we just heard Nagosa's talk. So from a more simple question then, there's a lot of exotic explanation here with magnetic graphene because of special band filling that then causes, you know, some of these effects. How is it possible that there's a much simpler explanation based on these previous theoretical analysis, or these previous talks, basically?
Yeah. So look, I mean, if you so I would say no. I think it's really it really boils down to I think here it boils down to that C2T symmetry. The combined C2T symmetry is somehow broken by interactions, by strongly interacting electrons, which somehow break these C2T symmetries. So I think this is maybe, I'm not sure if this was created in such a way in the previous talks. The previous talks had the feeling it was really engineered to break these inversion symmetries on purpose, for example, by making these heterostructures in a ABC sort of way or something like that, right? But those were more engineered effects. Here, I think the C2T symmetry breaking happens naturally from the interactions.
Okay, well, I mean, I think Nagosa was just mentioning, though, that if you break inversion and have strong correlations, that you can arrive at sort of this result. But maybe in a more simpler, even if I ask it even simpler, maybe I was being too complex. Like if you just fill to a random other fillings, not, I think you went to C equals 3 was the special one or something. The point is, if you go to a variety of these other fillings, do you still see, or do you not see this effect?
Oh, so again, as mentioned, so I think as you can see from this phase diagram, so we cannot tune so much way out of beyond the C equals -2 state. So if we, for example, we're not able to tune this device to all the integer fillings, but here in this particular case, as you already see, that we can at least cover -2 and -3, right?
Well, you shouldn't even have to go to another integer filling. I mean, just tune out of this one and watch the diode effect turn off, right? Is what I mean.
Oh, it is. So that's turn off here, right? So in the center, in the SFX region. So that's
well, that's not the diode effect, though. I mean, that plot is not showing the diode effect.
Oh,
like
so that's what I'm saying. So we
F and G and E are not diode effects.
No, but that's wasn't that your question, that we tune out of the diode effect? That's here. So here it's dead. There's no diode effect. Yeah.
I think
okay.
G, for example, G, for example, shows a diode effect.
So G shows a diode effect.
G shows an asymmetric Frauenhofer that I think Jia-Ching was also wondering about, right? But also, right, we are 5 minutes over the question session. So officially, I guess we should break. But so if anyone who wants to take a break can go take a break. And I think anyone who wants to just continue talking, if Dima wants to, we can continue talking. But officially, just so you guys know, you can take a break if you want.
So one thought I was having is that, and Dima, maybe you can comment on this. Yep. It seems like sometimes, particularly I guess in the SNS, but you can correct me, the resistance is not really getting all the way to 0, right?
Oh no, you mean in the entire Frauenhofer?
Some line cuts later, in a later slide. There were some line cuts that, yeah, let's see. Like these are good.
Oh, so you mean for the Frauenhofer, it doesn't go to 0? You mean these points here?
I don't remember which slide it was. It was a bit later than this one, but there was some. Yeah, here, for example, like there's a very gradual turn on. It's and maybe even at 0 current, there's at the finite magnetic field, there's a small offset. And the only thing I want to point out is that there is some theory that if you have a voltage, right, then you can also get interesting effects. Right, and normally the finite voltage is only relevant for retrapping current when a junction has really 0 resistance. When you're biasing from 0, then the voltage isn't there, so that kind of diode effect doesn't appear, but it'll come back on the retrapping effect. But here, since there is a bit of voltage present, as even when you're shipping away from 0, that physics might become relevant. That's just a thought of something, just something to think about. I don't know how relevant it is to the data, but it came to mind. That's all.